Okay, lesson 3.5, limits at infinity, and we put this in here just to keep all the limits together. So warm up, graph the function 1 over x, and write an equation for both the vertical and horizontal asymptotes. Alright, definition of a horizontal asymptote. If the limit as x approaches negative infinity of a function exists, and it has a value we'll call L, or the limit as x approaches infinity of the function has a limit and exists, and we'll call that L, then the line y is equal to L is a horizontal asymptote. And a graph can have, at most, 2 horizontal asymptotes. Now let's just recall the definition of a vertical asymptote. That was the limit as x approaches c of a function of positive or negative infinity, and the limit as x approaches c from the right of a function was positive or negative infinity. Then we would say a vertical asymptote existed at x is equal to c. So remember, vertical lines up and down, horizontal lines left to right. This behavior is known as an infinite limit. Okay, it increases or decreases without boundary. When we approach positive and negative infinity, that's a limit at infinity. Okay. So from last year, end behavior should seem sort of vaguely familiar. If I look at a function, the end behavior is exactly that. Ends of the graph of the function. As x gets bigger and bigger and bigger, so as x approaches infinity, what are the y values of the function doing? Okay, remember that limits are what describe y values. The limits are, the y values are getting bigger and bigger and bigger. That's what that arrow indicates. There's no end to the y values. Now, as x gets smaller and smaller and smaller, so as x approaches negative infinity, what are the y values of the function doing? They're decreasing without boundary. Because of this infinite behavior, no horizontal asymptote occurs on the graph. And looking at the graph of that function, we can see that very easily. So, let me draw something that looks like this. Now when I ask you for the end behavior of this function, as x gets infinitely larger, so as x gets bigger and bigger, the function appears to be leveling off at the line y is equal to 2. When I look as x gets infinitely smaller, so as x gets smaller and smaller, what are the y values of the function doing? They're leveling off at y is equal to negative 2. And this is why it was important to say a function can have at most 2 horizontal asymptotes. So there would be a horizontal asymptote at y is equal to 2, and a horizontal asymptote at y is equal to negative 2. So that infinite behavior still gives us very critical information about the graph of the function, but the limit itself, we would say, does not exist. Because the limits don't exist, there's no horizontal asymptote. Okay, we'll use this early and often. If r is a positive number, positive rational number, and c is any real number, then the limit as x approaches infinity is 0, and the limit as x approaches negative infinity is 0. Now let's see what this looks like. I have a number, any real number, and I'll say dividing by x cubed. If I ask you, think about this. As x gets infinitely larger, then I'm cubing it and making it an even bigger number. As x approaches infinity, my answer, 2 divided by a huge number, is just going to get smaller and smaller and smaller. Likewise here, right? Even if I did -1 divided by x, okay? X is going to get infinitely smaller. It'll become a more negative number. But at -1, any value divided by a huge number is going to get smaller and smaller and smaller. So we'll use this theorem often. Okay, to find a limit at infinity, and you did this last year, divide each term of both the numerator and denominator by the degree of the denominator, and then evaluate the limit of each simplified term. Remember what the degree is? Okay, term with the highest exponent. So determine the end behavior of each function. So the end behavior are the limits of infinity. Of x equals 4x plus 3 divided by 2x minus 1. It's a rational function, so it could have a horizontal axis. Limit as x approaches infinity. Okay, so according to the long way, we take the degree term of the denominator. Now you can include the coefficient, but you certainly don't have to. So we have 4x plus 3 divided by 2x minus 1. And we're going to divide each term of the numerator and denominator by that degree term. We have 4. I'm going to simplify each term. Now we find the limit of each term individually. Well, the limit as x approaches any number, real number or infinity, of a whole number is just itself. Using the theorem we just talked about, 3 over x, that limit's going to approach 0. 2 stays put, and this limit will approach 0 as well. Now, we can still use this simplified form. The 4 and the 2 stay put, and we know that the theorem remains the same as x approaches positive and negative infinity. These limits still approach 0. So what can we conclude from here? There's a horizontal asymptote at y is equal to 2. So that would be the end behavior. X equals 2x squared all over x plus 2. So end behavior is always two limit statements. Limit as x approaches positive infinity. I'm going to divide each term by x. So I get limit as x approaches infinity. I have 2x on the top. 0. But think about what happens here. As x gets infinitely larger and I multiply it by 2, my limit is just going to increase without bound as well. If I look to the case as x approaches number, so that'll approach negative infinity. Now, when we talk about the limit, again, the limits do not exist. And what does that tell us? There's no horizontal asymptotes on the graph of the function. Now, what this describes for us is just, because we will look at this, graphing rational functions, and it just gives us a lot of information about the graph of the function. F of x equals 4 plus 3 over x squared plus 2. Limit as x approaches infinity of the function. I'm going to split this up. 4 plus the limit as x approaches infinity, because we can do these limits, they have very nice usable properties. I'm going to divide each term of my rational expression by x squared. Notice that this 4 isn't affected by the x at all. That's why I can just set that statement as 4. And then this gives me, that'll always approach 0. So the limit as x approaches infinity will be positive 4. And as I look to negative infinity, looking at the simplified function, here, I forgot about my 4. This limit remains and then using what we simplified already, that limit remains 0. So there we have the horizontal asymptote at y is equal to 4. Okay, now the shortcuts, and this is what you would have learned probably last year more so than the dividing. To find a limit at infinity only. Okay, so these shortcuts will not work on anything we discussed in Chapter 1. Rational functions can fall into one of 3 categories. Top-heavy, where the degree of the numerator is greater than the degree of the denominator. They can be equal, the degree of the numerator is equal to the degree of the denominator. Or they can be bottom-heavy, where the degree of the numerator is less than the degree of the denominator. So the limits at infinity, if the function's top-heavy, won't exist. If the function is equal degrees, then the limit is the ratio of the lead coefficients. And if the function is bottom-heavy, then the limit is always going to be 0. So let's look at the shortcuts and we'll see how much easier this is for you. Compare the degree of the numerator with the denominator. Bottom heavy, so the limit's always going to be 0. Limit as x approaches negative infinity. 3 minus 2x all over 3x minus 1. Degree of the top, degree of the bottom. Now if you're using the shortcut, you do have to include the coefficients for this case specifically. The lead coefficients rather. So the coefficient in the numerator is a -2, so don't lose that, divided by 3. And if you use the division, the method we just did on the first few examples, you can prove that all these will get the same value. Limit as x approaches infinity, 3 minus 2x squared. Okay, top heavy, so the limit does not exist. Now, if we were talking about graphing the function, I would expect you to look at both cases of end behavior, because describing the behavior of the function, it will be different. So I'm going to do my dividing by x, 3 over x. This would simplify to 2x over 3 minus 1 over x. Okay, so if I divided every term by x, these approach 0. As I'm approaching limit, the behavior of the function will decrease without boundary. If I approach negative infinity, okay, using the simplified function, these approach 0, I would get -2 times some really, really negative number. So the end behavior there would actually increase without boundary. So your top-heavy case could potentially give you 2 different pieces of information about the behavior of the function. We can't just say it's always positive infinity or always negative infinity. Alright, let's look at 2 trig examples. So if I ask you the limit as x approaches infinity of the cosine of x, think about what the cosine function looks like, and sine for this matter. Okay, the cosine function, we know, has a range of -1 to 1. So this limit does not exist because of the end behavior of the function never approaches one single value. So it wouldn't be positive or negative infinity, it just doesn't exist. Okay, so this is going to be an important one, and it's going to be the same answer for cosine of x. In the interest of time, we'll leave this for class tomorrow.